I've been handling this coil for half an hour. You might wonder, what's this coil of, what that type of module? This is what we call the flex tube. And I'll now guide you through what is a flex tube. So basically, a flex tube, a cable, a typical flex tube cable, consists of specific modules here, specific buffer material that I'll explain further. And you see the fibers are very much in contact with each other. The module is very, very dense, very flexible. And this is encapsulating in many different designs in a sheath with radial strength members. The target has really been, initially this has been developed to tackle the challenges of the access where really space is scarce. You need to be compact. And also you need to be more handleable. You need to ease the tasks and work of the technicians, the people deploying the fibers in the field. So one of the first advantages, and I will circulate some of those modules, is there are different ways to open a micro module or a flex tube. One is what we call hand access or finger access. Means really you take your module and then you can open it like this and you have access to the fibers. And which is very, very interesting also is that we usually put some grease, some jellies in the tubes to protect the fibers. In a regular loose tube construction, you have a lot of gel, a lot of quantity of grease. So when you open with a tool, you need a tool to open first. And then when you open, you need to clean. And you have more grease, so it takes longer time to clean. Here, the amount of gel that is inside is pretty limited. So you really clean it very, very easily. And we even have developed this year a generation of flex tubes, totally dry, but okay, it's still at the stage of development, not industrialized yet. But already this version, you can have a look at it. You can even try and strip it with your nails. This version already simplifies a lot the accessibility to the fibers. And then a bit later, I will show you some comparative results that we made, access time between a regular loose tube design and this. Another big point is see how easy you can coil the modules. It's very flexible. You don't have a lot of form or shape memory, so you can consider having in connectivity, in joints. See here, for instance, a comparison between a loose tube and a flex tube. This is a 144 fiber loose tube design. And this is here, look the space it takes to coil 720 fiber modules here. It's very neat, very clean, and the coils are very easy. It's very easy to make the coils. And of course, as I mentioned earlier, the cross-section downsize, it's about 70% compared to a regular loose tube. We are way more compact, way denser. So indeed, and I've already touched, but you see the stories are all related. Huh? I've already discussed the additional compactness using band insensitive, but it's also using that type of module that we were able to pack so many cables inside one single duct. So just to visualize a bit differently, a typical loose tube design, cable diameter 25 millimeters for 720 fibers. And here, flex tube design, what we call mini design, and we have a micro and in development a nano. You see 720 fibers in 18 millimeters. So really densification of fibers, the number of fibers we can put in a given square millimeter. Another key thing, try and bend the modules. You will see that you can bend to very small dimensions without any kinking. While with loose tube, it's always a risk when you make your coils in connectivities or when you manipulate the modules to kink the modules. And when you kink them, once it's done, it stays. And there might be a risk here of pinching the fibers or of creating a stress on the fibers. This is something that's not happening with this material, with these flex tube or micromodule designs. Another thing, and beyond only words, I will show you experiments right after. These modules have an outstanding thermal stability. And again, in long distance, you hardly access the fibers in mid-span configurations. While in the access, it's been more and more common to really access some modules to make some branching out, some derivations, and leave other modules coiled in the joints, in the pits. And for this, you need to be careful, especially in some countries where you can get down to very, very, very low temperatures. You need to be careful that the modules that are left can withstand the very, very low temperatures. And with flex tube, we could really demonstrate an extraordinary thermal stability that I will, I'll explain further. I will give you some figures, comparative figures between loose tube and this flex tube material. So again, illustration of coiling a flex tube versus coiling a loose tube. How to open a cable? It's pretty straightforward. You just cut the jacket alongside the strength members. Then you use only simple tools. You remove this jacket, and the modules are ready to be opened. And the opening of these is pretty straightforward with these finger access capabilities. Another point is, and you'll learn more about this in what we call our our Verticasa configurations, where we could really leverage the properties of these modules to perform some side access to the fibers, some windows cut and extraction capabilities. Again, like for Retractanet, you'll have all the details of those solutions right after in Alessandro's presentation. So again, remember the organization of the sessions of today: fiber, buffer materials for modules, and systems and connectivity we can use. So this is the stream of today's information. Getting into some comparative tests. More details. We've tested several things. We tested first end access. I'm having my cable, loose tube cable on one side, flex tube on the other side. How long does it take me to access the fibers? Exactly the same for mid-span access. How long does it take me in the two designs to access the fibers? Then, okay, another picture for the kink effect, and some thermal cycling results, comparative test between loose tube and flex tubes in this mid-span access configuration for the express modules. And access. What we've done is we took the two designs, loose tube, flex tubes. Step one, we opened the cable jacket over 1.5 meters. Step two, basically we removed all the unnecessary cable elements, cut the yarns, cut the ripcords, the tapes. So basically eliminate everything to be totally clear and neat for the modules we want to open. Step three, we removed the buffer material. And step four, we just cleaned the jelly off the fibers. And then we were ready for splicing preparation. So 4 steps. Here, You have a picture of the tools that were used for the flex tube. The opening with the ripcord here, the opening of the jacket. Buffer removal, okay, there are different ways. Here it's shown a buffer removal, just taking some material and slipping it all across the fibers. But okay, there is another way that is used in field. It's basically using the fibers as a ripcord. You take the fibers and then you can strip the module and open on a long distance also. And then fiber cleaning, so paper, and then you see a limited amount of gel here, obviously, because the size is very, very small. So not so many gel inside the tubes. For loose tube, we need one additional tool, especially here, for opening the modules. So jacket stripping, buffer removal here, with the tool around the loose tube module, and the cleaning of the jelly. And you see already, more quantity of gel. Of course, it's bigger. This chart is a bit busy, but details you the measurement of the time to access for the different steps. Step 1, removal of the sheath. Step 2, removing all the cable elements. Step 3, removal of buffer tubes. And step 4, cleaning the fibers. Here, we've tested 2 designs of cables, basically. One 6-module cable, so more smaller design, and one 24-module cable. Flex tube on the left, loose tube on the right, and then you see here in minutes the different time it took for the different steps. In total, in those 2 configurations, flex tube was between 30% and 40% quicker to access compared to equivalent loose tube design. After the operation of end access, we've conducted mid-span access, so exactly the same steps, just that it's take a bit longer because we open not on 1.5 meter but on 2.5 meters, so we have more module and fiber length available. So step 1, removal of cable sheath. Step 2, removal cable elements. Step 3, selection of the modules we want to branch out and make a proper coil of the modules we want to leave untouched as express modules. Step 4, cleaning off the jelly, and step 5, preparing this coil for remaining modules. Again, some pictures, flex tube, jacket stripping, another one for jacket stripping here with a ripcord, buffer removal, again the same for flex tube, and here you have a picture of mid-span access finished, that is to say here the fibers prepared to be totally open, prepared to be spliced, and here the coil of modules prepared for the express. For loose tube, here jacket stripping, cutting the binders, maintaining the buffer coil because it's more difficult with loose tube, so you need to maintain it and put some binders here. And then this is prepared, mid-span access finished with the express modules and the fibers for being prepared and open for splicing. Just another view for the 24-module cable. So you see the amount of loose tube you need to deal with. It's a bit bigger. So it's taking some time to make a proper coil and to put the binders. And okay, this is once finished with the loose tube material for the 24-module design. Again, comparison here. You can see the different steps. And you can really see here in this configuration, the key benefit of flex tube, just because also you save an additional time in the coiling of the uncut module, the express modules, and so 50% time saving, which is significant when you have to deal with many preparation and access and splicing in field. This is significant amount of time that you'll save, your installation crews will save. So again, after 12 minutes of preparation, this is it for flex tube, for loose tube, and for the bigger ones, 24 modules here, coiled, the fibers to be accessed, and here, after 37 minutes compared here with 20 minutes, this is what you have, loose tube, flex tube. So pretty obvious. In summary, here, a view of the, on the top, end access measurement, on the bottom, mid-span access. For the two configurations, the smaller cables, the 6 modules, and the 24 modules here. Flex tube in violet, loose tube in blue. So you see in all cases, 100% of the cases, we were quicker accessing and preparing the cables for installations. Kink, just another view of kink potential or non-kink potential of the flex tube material with a ruler here. You see, you can, this is, 10 millimeters. So you see the amount of capabilities we have with flex tube. Basically, the material is just tolerant to kink. There's nothing happening. While with loose tube, already here, you see 30 millimeters being, you can have some incidental kinks. And last, thermal cycling. So what we did is, again, we prepared the coil of modules for the express here. We prepared it properly, put binders, and then we put it in a temperature chamber here, and we measured the optical performances in terms of attenuation variation over different temperatures. So room temperature, this is the blue curve here. Room temperature, minus 40, plus 70, room temperature, minus 40, and so on, and so on, and so on. And we checked the attenuation of all the fibers in the module. And what's put here is the maximum attenuation that could be monitored over all the fibers inside the modules. And for the flex tube, we could really see, and especially remember the first presentation, the upper band, the L band, what we call the 1625, the long band, is more sensitive. So when you want to see something, try and monitor the attenuation variation in the long band. It will magnify all the effects. And in the long band, we were able to monitor 7 times better performances with flex tube compared to loose tube. Again, this is a very, very, very good cable structure for the access, for the handleability, for the compactness, and its capability to withstand temperature cycling, temperature variations. So before I give the floor to Jack, so Jack can present to you some more local capabilities for flex tube. I just wanted to conclude a bit on this flex tube. So again, you recognize the chart which I've presented during the fiber part. This cable has been made possible, the very small designs have been made possible leveraging super fibers, I mean band insensitive plus excellent coating, and those micro module designs that are very, very, very powerful to condense the size of cable elements. And what we do think, and really it's like any new technology, it didn't come up in 1 minute like this. It's just, micro module has been basically invented in the mid-90s, but then for a technology to make it through in real deployment, you need to qualify it, perform many, many, many different tests with many, many operators just to be sure everything is fine. And the big first deployments happened, I would say, mid-2000, so 10 years after it was introduced. And now we can really see it picking up in volumes because it has obvious benefits. Then it's all about figuring out, yeah, but it's so teeny, so small. Is it really stable, durable? Yeah, you need to get your hands on these modules, test them, but you will see the benefits are obvious, and the impact for the access network also obvious. And we do think combination of these micromodules plus band-insensitive fibers and optimized coating are the top quality material for durable access networks, because really simplifies many, many different operations and preserves over the years performances. So this is it. Jack will now guide you through what's possible in terms of the FlexTube material in here, this region. Again, any question, feel free to interact or to come and see us during the break so we can discuss further these aspects. Thank you.
Okay, thanks, Elaine. Okay, we'll get a bit more practical now. So FlexTube, well, we're very excited to have FlexTube as part of our portfolio now in Australia. We're seeing a lot of interest, particularly in the built-up metro areas, the congested duct pit networks. This is really a great solution for that. Just from the sheer size of the cable, you look at now we're looking at fiber counts up to 1,728 fibers in a single cable. We can compare that to the ribbon architecture that NBN are rolling out. That's 864, so less than half the fibers in a much larger cable. So FlexTube, we really see a lot of potential in the congested areas of the metro CBD in trying to ease some of that congestion and continue a fiber rollout with limited duct space. That's the first probably reason that we're getting the interest in Australia, the first reason that people are taking it up. But then you look at the ease of installation as well. We like to think about the total cost of ownership of a fibre network, and that's what Richard touched on with his opening slide. Things that you may not see as obvious straight away, the ease of removing the buffer material with your fingertips. I encourage you to have a go when you get a chance in the break. And the ability to strip large quantities of the buffer tube. As Elaine said, almost using the fibres as a ripcord. You can strip them very, very easily. And that just speeds up the rollout, speeds up the amount of time the guys in the field are taking to prepare the joints. So if we compare a FlexTube and a standard loose tube cable, I mocked up a couple of joints. Probably the most professional cable preparer, but I gave it a go. Anyway, our SmartCore loose tube cable range, mid-spanning that requires a tool to cut the tubes and remove them. Then you have to clean all the gel and everything. With the FlexTube, you maintain the tubes, you coil them up into very small bend radius, and you can store them at the back of the joint. Very quick and easy to do. So you cut all the time from having to clean the tubes out of the build. And of course, then you've got the protection around the fibres, which continue to protect them inside the joint. When you have to remove the tubes, obviously there's a risk that you could cut the fibres and potentially damage them. So there's lots of other benefits that aren't as obvious, apart from the size of the cable, which is reasons why our customers are taking them up at such a high rate. So looking at that in a bit more detail, over 40 countries have already benefited from the capabilities of FlexTube. So by no means is Australia the first. It took off really in Europe, in France, where it was first conceived and invented, if you like, and they're rolling out only FlexTube in the access network now. They don't use any loose tube at all, just because of the benefits that the product gives you. It's fast becoming the technology of choice, and as you'll see later this afternoon, that technology of bunching fibres into modules and then put them in the cable has then allowed us to come up with a whole ream of different products, the Retractor-Net, the Verticaster that we'll come to later this afternoon, which all benefit from essentially having that fibre available. So without the fibre, we couldn't do any of this. Without an advanced low-loss fibre, bend-insensitive fibre, we couldn't put them into very, very small packets like we do, and we wouldn't have the cable range that we have. So it's down to the fibre that we can be thankful that we can generate these innovative cable designs. So we've got only over 250 kilometres of cable deployed to date in the local region. Significant quantities of FlexTubes installed in the last 2 years. Other customers are now planning further deployments as they're realising the benefits. I suppose if you were to go from a standard loose tube cable to a FlexTube, I mean, telcos by their nature can be a bit conservative when it comes to coming across a completely new design, and it is very different to a standard conventional loose tube cable. There is going to be a bit of caution there as how we prepare the cable. There's going to be a few new skills to learn from the installers, but once they get over that, the rate of rollout is so much faster that it makes the transition really, really worth it. So that's the reason why we've got 250 kilometers under our belt already in the last couple of years. If you incorporate then again the 200 micron fiber technology, you can look at condensing that cable even further. I mean, I can't think of how we could really design a cable that could pack any more fiber into a given area any more than FlexTube. FlexTube is really allowing us to minimize that cable OD, package the fiber in those small modules, and as Elaine touched on, we're now looking at reducing the size of these skins, these modules that surround the fibers, and that again brings the cable down further in size. So it's all very well having a fantastic cable solution, a small, flexible, and easy to prepare cable, but you need the connectivity to match it as well. So I guess what we're excited to have now is Matt Carryover from the UK, who's brought over the latest in cable perforating joints and enclosures that allows us to really reap the full benefits of a FlexTube cable and to be able to store that huge amount of fibre in a very small enclosure. So Matt, should we run through a few of the joints now?
Yeah, let's go for it.
So as I showed you there, that's one of the joints and a comparison between the conventional loose tube and FlexTube. But Matt's also got a couple of different other ones, one that's a bit larger as well that we can talk about now.
So yeah, so we've got basically a new family of joints that are optimized for the FlexTube cable. It's just not to say that the loose tube isn't compatible. The loose tube is fully compatible with these joints, but they've really been optimized from the initial design for the FlexTube cable. So we'll start with the CMJ. Jack briefly held up a moment ago, but it's a 144 fiber compact joint, 12 single element splice trays, loop storage on the back, as you can see for the FlexTube mid-span access loop, but also a 288 fiber version, which has 24 splice trays, again single circuit, and capacity for a larger loop on the back. The main real sort of key features for this joint, I would say, would be the mechanical sealing system. Certain territories are moving completely away from a heat shrink gland or a heat shrink cable sealing sort of technology. They're going to a mechanical sealing system. Particularly in the UK, British Telecom asked us to develop a fully mechanical seal to basically mean that they don't have to have any of the gas, any of the flame canisters basically carrying in their vans. So we developed our system initially for the circular port and also moving on for the oval port as well, which is technically a little bit more difficult. But basically, our system comprises of a main gland body with a sealing grommet inside, some compression fingers, and a clamping nut. On the other end, a removable widget, which is specific for the style of cable that you're using. So a loose tube cable, for example, with a central strength member, would have a certain style of widget. The flex tube, again, would have a different widget. A blown fiber tube would have something completely unique for that type of cable. So the idea being that all of the cable preparation can be done remotely away from the joint and then just plugged in to the joint. Basically, it gives you fantastic access to do everything remotely where there's space, and then just bring it into the joint, clip it in place, and it's fit and forget. So in the break, come and have a look. Obviously, I can't go into too much detail because you guys are all over there, and I'm here. So come and have a look in the break, and we'll go through in some more detail. But just moving on to larger format joint, the LMJ, which is a large multifunction joint. It's in the configuration we have here with 80 splice trays. It is basically suitable for 960 splices. We also do a version with 24 splices per tray, which allows us to splice up to 1,920. But really, this sample is we've brought it across because we've installed a 1728 flex tube, and it's a great example of how neat the cable is, and the connectivity is really benefiting from this style of cable. come and have a look in the break again, because it's a really neat solution. But a couple of the other features, I mean, it uses the same mechanical sealing system as our smaller joints. In this instance, the oval port is also mechanical. It has space for loop storage of a 288 fiber loose tube cable or 720 fiber flex tube cable. But also it's fully modular. As you can see on the schematic on the right here, you can start with just 16 splice trays, but then in the field you can modulate the joint, so you can add 32 tray additional upgrade packs to a total of 112 splice trays as required. And also the footprint of the joint in the joint box is kept to a minimum, because you can upgrade the cap at the same rate. So there's no need to be taking up any more space in the joint box than you absolutely need. So if you're unsure what your network utilization is going to be, you can build on as and when you require.